Hello, this video is for Unit 7 Biomechanics in Sport and Exercise Science, and it's part of 7.3, assignment 7.3, looking at angular motion. This time we're looking at angular momentum, a term which hopefully you recognise from 7.1 where we looked at linear momentum. So just to recap from 7.1, what is meant by linear inertia and linear momentum? Hopefully you recognise that inertia is the resistance to change any object has, a resistance to change its motion. So if an object is stationary, it doesn't really want to move. If an object's moving, it doesn't really want to change its velocity. And how much inertia an object has is based on its mass. Momentum, hopefully again you remember, is the amount of motion an object has, and it is related to two things: one, its mass, and two, the velocity the object is travelling at. If it's got a greater velocity, it will have greater momentum. If it's a bigger mass, it has bigger momentum, and vice versa. So, question then. Here is Tom Daly performing some rotations in his high dives. Now, first of all, the task would be for you to identify which planes and axes is he rotating in and about. And the second question would be, which of these three would be the easiest for rotation? But importantly, could you figure out why? So hopefully you recognise that both of these two, he is rotating basically in a forward or backward spin around the mediolateral axis, so a side through side axis, imaginary line if you like, and he is spinning in the sagittal plane. So he's spinning in the sagittal plane in those two through the side to side axis. This one, however, on the right, he is rotating almost long and thin. So he is spinning around the longitudinal axis that runs right down through his body, and his body is rotating around it. So that answers the first question. And that, of course, is in the transverse plane. Which of these is easiest for rotation and why? Well, this axis would be approximately here, just sort of, I guess, by his chest. The axis would be here about his chest. This one going down through the middle. The reason this is the correct answer for the second question, this one would be an easier rotation, is because his body in this direction is really narrow. The axis line goes down through the middle, and the distance from that axis, that pivoting axis, to where his mass is spread is a relatively small distribution. Whereas from here, the axis going through the side to side, he's got toes out there, head out there. It's a longer distance. His mass is more spread out. And this one over here, even more so. If the axis was going side to side through here, he's spinning around it. He's got legs out there, and a good bit of mass out there. So his distribution is probably most spread on the left, in between in the middle one, and most narrow and most near, close to the point of axis on the right hand one. So this one he should be able to spin easiest. And this, I guess, goes back to why do divers tuck so tight to try and reduce that distribution of mass and get it as close to the line of axis as possible, that rotational point as possible. The more spread out they are, the more difficult it is to spin around the axis. So, some angular terminology. Now we know that linear momentum was how much linear motion an object has. It makes sense that angular momentum, therefore, is how much, the quantity of angular motion possessed by an object, by a body. So how much motion does an object have whilst it's rotating in angular motion? Now, the measurement for this is related to mass and velocity. So we've got kilograms per meters per second per rads per second. Now, linear momentum was mass times velocity. How much mass does an object have? How fast is it travelling in terms of velocity? Angular momentum is similar but a little bit different. So we have angular velocity the same. Angular momentum is moment of inertia times angular velocity in rads per second. So that's pretty straightforward. That's the equivalent of the velocity in linear motion. But instead of having mass we've got this phrase moment of inertia, and its unit is kilograms per meters squared. So angular momentum is moment of inertia times angular velocity, measured in kilograms per meter squared per rads per second. So it's quite, the units are quite a mouthful, but you can see that they combine the two components of angular momentum. I think this will be best understood when we have a look at examples. So even without sort of numbers within our examples, this diving example can give us a clue. The diver leaves the diving board and immediately gets into a very tight tuck position. And what we hopefully know already is that they're rotating around the mediolateral axis that would be sort of going through side to side through their body. And part of the reason they get into such a tight tuck position, or pike position in this example, is so that they are as close to that rotational axis as possible. What that means is the moment of inertia is quite small and the angular velocity is quite large. So this omega sign means angular velocity, i.e. the tighter they tuck, the faster they spin around that axis. But when the diver wants to sort of approach the water and go into the water, they need to slow down their rotation. So they need to reduce angular velocity. And the way they achieve that is that they open out their body. So that point of axis would be about here, and they are distributing their mass more widely. So at this point, moment of inertia is much greater and angular velocity is greatly reduced, and at this point stopped. They're not rotating anymore because of their body position. So hopefully even from this you can see a connection between moment of inertia, which is basically how distributed your body mass is. Is it tight to the axis point, or is it spread out away from the axis point? That affects your angular velocity, how quickly you'll spin. So some key terms and definitions for those things. Moment of inertia is the resistance of a body to change its state of angular motion. Remember linear motion, inertia, objects don't want to change motion, they want to be still, or they want to keep moving, they don't want to change. This is exactly the same principle, but in terms of angular motion. Objects don't want to change their angular motion, they want to just stay as they are. Importantly though, this is related to two things. The mass of the object, which is the same as linear, but more importantly, the distribution of that mass about the axis of rotation. So elbow, okay, over here we've got, if we looked at flexion and extension at the elbow, so what were downward movements of our forearm, we've got this mediolateral axis, but our limb is quite long, our forearm is quite long, and so that's got relatively high moment of inertia because the mass is quite highly distributed. It's distributed quite far away from the axis of rotation. So velocity here would be relatively slow because the forearm is quite long and the mass is distributed far away from the axis of rotation. If we look at the radial ulnar joint, where we do supination and pronation, so the axis of rotation here is along our forearm, along our radius and ulna, and would be longitudinal, the longitudinal axis. So what we all can see hopefully is that K here represents the distribution of the forearm away from this point of rotation, this axis, and it's a tiny distribution. The mass of the forearm is all really close to the rotational axis line, which means that for supination and pronation, the moment of inertia is relatively small, so K is relatively small compared to the flexion extension example, and therefore angular velocity can be higher. And of course the same as I've already explained the example of our diver over here. So this is the axis line, rotation going through there. This is a sort of a medium, this is the smallest moment of inertia, the most tightly packed tuck position, trying to get the body's mass as close to that axis point as possible, which means that we've got a low moment of inertia and a fast angular velocity. Here's an in-between one, the pike position. So the athlete's mass is slightly more distributed away from the axis of rotation. Therefore, moment of inertia will be a bit higher and angular velocity a bit lower. Here we've got a really extended position where the athlete's mass is highly spread out, distributed more broadly, which means that they will rotate much slower in this position. So, calculation of moment of inertia. Moment of inertia is the sum of mass of the object times the distribution of the mass from the axis of rotation. And it's this equation over here. Moment of inertia is the sum of mass times the distribution of mass from the axis of rotation, r squared, radius squared. Now, I wouldn't be quite so mean as to make you calculate moment of inertia. I've given you the information that you need. 60 kilograms, so that's mass. Diver performs a tucked reverse somersault. In the tucked phase, their moment of inertia is 15 kilograms per meter squared. So I've given you a moment of inertia. You need those two values, of course, and then they rotate with an angular velocity of 8 rads per second. What's the angular momentum? So there's the equation. Angular momentum is moment of inertia times by angular velocity. So hopefully you recognise that moment of inertia is 15, angular velocity is 8, times those two together, you get 120 kilograms per meter squared per rad per second. So that example describes how much motion there is. But let's just look at how we generate angular motion. Why is it that divers don't actually execute vertical jumps? They typically lean backwards to leave the board. Well, that's because they've got to create that rotational motion. If they just jumped up, they would jump vertically up and vertically down, but they've got to create that spinning, rotating action as they leave the dive board. Now, you may remember from forces that you can apply a direct force through center of mass and you get linear motion. If you apply an eccentric force outside of the center of mass, you generate angular motion, and that's what they do. They lean back, they push off just outside of their center of mass, and that's how we get rotational motion. That's how we cause rotational motion. The same would be true of this forward roll example here, of course. Center of mass is here, slightly moves forward as the gymnast begins to initiate their roll. They push off the ground. An eccentric force is applied behind or above the center of mass, creating that rotational motion, and then they carry on the spin there. Obviously, how much eccentric force you apply determines how much rotational motion you generate. This rotating force is actually called torque. So the amount of force applied to an object to make it rotate is called torque. The greater the torque, the greater the momentum. And for many diving and aesthetic performances, so figure skating, gymnastics, in order to create enough momentum, you have to leave the ground generating it. So that eccentric force, that torque that you generate really matters, because once you're in the air, once you're in flight, you can't change that. You can't apply any greater force. What you can do is manipulate your body position to reduce the moment of inertia. You can't increase the velocity, you can't increase the force to spin you round, but you can manipulate the moment of inertia by your body position to try to increase angular velocity. Now, without doubt, in class, we'll give this a go. If you sit on a wheelie chair, an office chair, and you spin around with some mass very close to this longitudinal axis, what you're basically creating is a low moment of inertia, so the small I, which will make you spin around quite quickly, high angular velocity. If you suddenly stuck your arms out, what you're doing is distributing the mass further away from the longitudinal axis, which increases the moment of inertia, big I, and slows your angular velocity, small omega. So the distribution of mass very, very much influences velocity or angular velocity, your spinning speed. If you have watched ice skaters, they chop and change their body position. They'll spread out, they'll get really narrow and spin very, very quickly. This is the physics of motion. So this graph shows very clearly the interrelationship between angular momentum, moment of inertia, and angular velocity. How much motion we have, how distributed our mass is, and how quickly we rotate or spin. First of all, hopefully you've noticed that angular momentum remains constant throughout this reverse somersault. But how we achieve that amount of motion varies. So at the start of the skill or technique, we've got a very low angular velocity. We're not spinning very quickly here, and that's because our body is quite spread out. So the body is very open. The moment of inertia is quite high because the body is distributed far apart from the axis of rotation. However, by the middle phase of the somersault, when the athlete is tucked tight, what we see is that moment of inertia is reduced dramatically, which means that they can spin much more quickly and angular velocity increases. And of course, when they're getting ready to dive and enter the water, they want to reduce the angular velocity. They want to spin less. They want to actually stop spinning. And the way they achieve that is by increasing moment of inertia, stretching out their body, elongating it, distributing it far apart from the moment of inertia. So that graph shows that nicely. And of course, there's my ice skating example. There are loads and loads of examples whereby we have big moment of inertia, small moment of inertia, low velocity, fast spinning, high velocity, angular velocity, and so on. Again, take off, big moment of inertia, tight tuck, low moment of inertia, open up, slow us down, again, big, high moment of inertia. So all of these body positions and the way you have your limbs and how you distribute your body around the axis of rotation is basically us manipulating our moment of inertia, which in turn influences our rotational angular velocity. There's just an A-level mark scheme you can take a look at. It breaks down this question. Explain how a figure skater controls angular velocity when performing a multiple spin around the longitudinal axis. Exactly what we've been talking about. So, just to be clear, once angular momentum is generated at takeoff, once you leave the ground, your angular motion, your angular momentum is constant. It doesn't change. But what you can do is manipulate the moment of inertia, your body position, so that you in turn change the angular velocity. So all of these diagrams are illustrating pretty much the same speed. It doesn't mean you travel through the air quicker. It means you spin in the air quicker. Last little example. If you were asked to run with straight legs as fast as you can, I'm pretty sure you'd find it quite challenging. So the axis of rotation is your hips, mediolateral axis, and your hips are basically doing flexion and extension to move you. So if you think about legs being straight whilst you're running, there is a very high distribution of mass. So your limbs are spread out quite far apart from this axis of rotation, as opposed to our normal running technique whereby we bend our knee to bring the limb forward. Rather than keeping it straight, we bend our knee, and all of a sudden what we've got is this axis of rotation and our mass being distributed much nearer it. So by bending our legs, we move our limb forward quicker. We have greater angular velocity at the hip joint because moment of inertia has been reduced by bending our leg. This was an A-level question which essentially addresses that point. Explain why a runner has a flexed knee during the recovery phase of the stride action. And it's because they're reducing moment of inertia and able to rotate, flex forward, rotate at the hip joint quicker, angular velocity quicker because of that moment of inertia reduction. So throughout the whole assignment of 7.3, remember you're going to give a variety of sports examples for one of your examples, and you must give one gymnastics related example also to show your real understanding of all of these principles.